All right, so for part C, for part D, we're now going to be looking at Dijkstra. Okay, so here is the graph. I'm just going to put it down at the very bottom because I want to fit this table at the top. Okay, so this table is really the way that you will keep track of the shortest path distance from the start vertex to that vertex so far, and the predecessor along that shortest path. And so because our start vertex is A, we will change this distance value to be 0 in the beginning because the distance from the start vertex to the start vertex is 0. And everything else is going to be initialized as it is to infinity. And again, the reason why it's infinity is because if it wasn't infinity, right, then we would never be able to update any of these shortest path distances because we only update when we have a better, shortest path distance, right? And so, for example, if we had negative infinity, that's probably the smallest you could ever get. In fact, you can't have any negative distance. It doesn't make sense, but theoretically, if you had negative infinity initialized, then you would never update anything. Okay, so that's in the first iteration, right? So in the first iteration, we update A to be shortest path distance 0, and we know that its predecessor is going to be itself. You can either denote that by putting A here or just not having anything. Either way is fine. But we need to now branch off. Okay, so what are all of its neighbors? It has an edge to B, has an edge to E, right? What is the weight on these edges? Now we're using weights. So B has a shortest path distance from A, 1. Okay, that's a lot better than infinity, so let me update that. And actually, sorry, this should be in the second iteration. So basically, the updating is going to come in when we pop off A from our priority queue, okay? And so the popping off of the priority queue denotes that the shortest path distance for that vertex is fixed forever. We're not going to go back and change it later on. We can't. So I'm going to denote that as an asterisk, okay? And that asterisk kind of signifies that it's the optimal shortest path distance found by this Dijkstra algorithm, okay? So once we have popped off A, we now look at all of A's neighbors, which are B and E, okay? B has a shortest path distance of 1 from A, and E has a shortest path distance of 3 from A, and everything else is going to be as they are. And yeah. Okay, so now in the third iteration, this is optimal, so again, we don't change it. I'm just going to denote it with a slash. And we need to now pop off the vertex with the greatest priority, which in this case means the lowest priority value from our PQ. What is the vertex with the lowest priority value? Well, what is our priority value? Our priority value is the shortest path distance, right? Whatever is in front of these parentheses. I forgot to mention that the parentheses denote the predecessor, and the number in front of the parentheses denote the shortest path distance so far. And so the node with the lowest priority value is going to have the highest priority. In fact, it's going to be the first one popped off from the queue, right? And so in this case, it's going to be the node B. So we pop it off. In other words, we make it optimal. We make it fixed. And then we look at all of its neighbors. We have C and F, right? So what is the shortest path distance from A to C through B? Well, B's shortest path distance from A is 1. So C's shortest path distance coming from B must be 1 plus the weight of the edge between B and C, which is 2. So 1 plus 2 is equal to 3. 3 is much better than infinity, so we're going to update that. And we're going to have the predecessor, the immediate predecessor of C, BB. And then everything else for D and E stay the same, as well as for G and H, because they are not neighbors of B, right? So they don't have a chance of being updated. Whereas for F, that is another neighbor of B. And so let's look at the shortest path distance for F. It's going to be the shortest path distance from A to B plus from B to F, right? So we already have what the shortest path distance from A to B is. It's 1. And then the edge weight of between B and F is 4, and so 1 plus 4 is 5, and so this is going to be updated as 5. The predecessor is going to be B. Okay, and so in the fourth iteration, now these two stay the same. We don't change that. And now what is the shortest vertex from, sorry, the highest priority vertex from our queue? It's going to be either C or E, right? But in this case, we break ties lexicographically. So we're gonna pop off C first. So we're gonna make this optimal, okay? Which means we look at all of its neighbors. We have the only neighbor being F, and so what is the shortest path distance from A to F through C? It's going to be 1 plus 2 plus 1, right? So basically the shortest path distance from A to C, which is 3, plus the edge weight between C and F, which is 1, that's gonna come out to be 4. Is 4 better than what F has currently? Yes, 4 is less than 5. We want it to be smaller, so we're gonna update this with C being the new predecessor, and then everything else stays the same because no other vertex is a neighbor of C. Oh, sorry, that should be 3. Okay, and then in the fifth iteration, what do we pop off next? We pop off the E, that's the smallest, shortest path distance. And from E, its only neighbor is F, right? And what is the shortest path from A to F going through E? It's 3 plus 7, which is 10. That's worse than what we have for F right now. So we're not gonna change F, and we're gonna keep everything else the same. So now in the sixth iteration, we are going to pop off F, okay? And from F, we have neighbors D and G, right? What is the shortest path distance from A to D? Well, it's the shortest path distance from A to F plus the weight between F and D, which is 2. So that's going to be 6 for D. That's better than infinity. Predecessor is now F. And then for G, it's 4 plus 4, which is 8. And that's also going to have predecessor F. And then H is still infinity. Okay, so I'm kind of running out of room here. But in the seventh iteration, we're going to pop off the D. Now this is going to be fixed. And if we look at all of the neighbors of D, which are G and H, is the new shortest path distance for G better than what it has already? Well, let's look. G's shortest path distance is going to be D's shortest path distance plus the edge weight between D and G, right? So that's going to be 6 plus 1, which is 7, which is better than 8. So now we're going to update this with the new predecessor D. And similarly for H. H is now going to be 6 plus 4, which is 10, which is a lot better than infinity. Okay, so now in our 8th iteration, we're going to pop off the G. Okay, and from G, can we update H to be better? Well, H is now going, the new value for H is going to be 7 plus 5, which is 12, which is worse. So we're not going to update H, we're going to keep it as it is. And so in our 9th iteration, we're going to have everything exactly the same. Okay, so now this is also going to be optimal. So once you have every node an asterisk, right, then you're done. Okay, and so this is going to be the shortest path tree. So how do we trace back the shortest path tree? Well, let's we basically need to look at the predecessor, right? So we start at the start vertex. Whoops. Oh, okay. And then we go to B. We can also start from the bottom as well. And then from B, we go to C. Okay, so my shortest path tree is what I'm doing in blue. And then from C, we go to F. Okay, so I'm basically looking at which node has predecessor C. And then from F, we go to D. And then from D, we go to G and H. And E has predecessor A, so it must look like this. Okay, so that is the shortest path tree.